Hello, we're Team 2 from Fundamentals of Nuclear Engineering Section 2 with Dr. Tris Uchchik. I'm Garrison Lanham.
I'm Cesar Mayorga.
I'm Adrian Salguero.
I'm Shasta Brundage.
I'm Sebastian Yabui.
And today we're presenting our reactor simulation project.
In this exercise, control rods are manipulated from 2% insertion into the core up to 50% and how it affects thermal energy output, steam generation, and pressurizer conditions.
Looking at the graph in the top left corner, as the position of the rod gets lower, the core thermal power also gets lower as well, which means you are producing less heat, then less heat is being transferred into the coolant loop, as displayed in the top right graph. In the bottom right graph, there is less steam in the steam generator, which reduces the movement of the turbine. The pressure in the steam generator is increased due to the decrease in the core thermal power caused by the pressurizer maintaining its initial pressure, as displayed in the bottom left graph.
The temperature and pressure vary slightly in the pressurizer, but overall maintain a steady 2,268 psi throughout the simulation. They do not change because if pressure is not changed, then the temperature has to also remain unchanged. This is due to water in the pressurizer maintained in a saturated mixture state and at a constant pressure. In this state, the pressure and steam have to stay within the saturated liquid and vapor line that is under the bell curve.
In exercise 2, turbine demand percentage was manipulated to control the reactor power output. We're going to discuss how the turbine demand affects the thermal power production, pressure within the steam generator, and the control rod position. Looking at the bottom right graph first, you can see how turbine demand was changed over time. In the top left graph, you can see how rod position relates to turbine demand. As turbine demand decreases, the rods lower into the reactor. As turbine demand increases back to 100%, rod position increases back to 96%. This occurs due to the decrease and then the increase of the core thermal power based on the turbine demand. In the top right graph, the core thermal power is displayed. It directly reflects the turbine demand as it is changed. This is because the turbine demand controls the power output. So when you increase the power output of the system, the power of the reactor generates has to increase. Finally, in the bottom left graph, you can see how the steam generator pressure changes based on the turbine demand. You can see an increase in pressure as turbine demand goes down and a decrease in pressure as turbine demand goes up. This occurs because the coolant temperature and turbine demand have an inverse relationship.
Reactor leading is the best method to use for stable reactor control. Changes occur faster with turbine leading. When changes occur within a reactor, they need to occur at a slower, constant rate so that the reaction can be easily controlled. Since changes occur so quickly in turbine leading situations, steady state level is often overshot and has to be normalized. When these changes occur quickly, there is a possibility of major malfunctions occurring. Large changes occur in coolant temperature and steam generator pressure with turbine leading situations as well. These large changes occurring quickly are why the turbine leading situation is not preferred.
In exercise 3, we simulated an emergency reactor trip. We will discuss how the reactor trip affects the fuel temperature, power neutron flux, and the steam generator pressure over time.
The graph on the left shows a big drop of the fuel temperature and levels out to a constant value of 500 Fahrenheit. Meanwhile, the power neutron drops considerably from 100 to about 0 and levels out. The steam generator pressure in the at the same time increases from 708 psi and levels out at 150. This condition occurs because of the drop in power generation due to the trip of the generator.
The profound change in reactivity is due to the control rods being inserted into the reactor to cool down the system. With this increase in pressure, the coolant is unable to lose heat in the steam generator because the water in the steam generator is unable to reach its boiling point. In the system, the coolant temperature and the reactor temperature converge at about 577 degrees Fahrenheit. Then it is unable to lose any more heat through the coolant loop due to the high steam generator pressure. Are there any questions? Any questions at all?